in addition to summarizing our data sets using measures of central tendency and measures of dispersion, we can also look at different graphic displays. And so we'll talk about a few of them here. Again, we could devote a lot of time just to graphics, but I just want to just give a brief overview of a few of the procedures and not get into a lot of the mechanics of them, but so that if you ever see them, you know what's going on with them. All right, the first is referred to as a box plot. Some refer to it as a box and whisker plot. Okay. The advantage to these is that they do illustrate both central tendency and dispersion. They can, these are oriented vertically, but they could also be done horizontally. So here I have a box plot for each of 3 groups, and I'm illustrating a few things about them. Okay. First of all, you'll notice the box, hence the name box plot. Okay. So your low, here from the low end to the high end on the scores, the vertical scale over here is measuring the responses. All right, and we have the lower edge of the box corresponds to Q1, or the first quartile. The line across the middle of the box is Q2, or the median, and the top edge of the box is Q3. So at a glance, you can get what the interquartile range is. Okay, how spread it, so we know 50% of the data lies within the length of this box. Okay, this one I didn't request it. The means can be printed on these, and so they're usually given a different symbol, and so in this case I'm going to use a plus sign. Here the mean is 4.42, so it's somewhere less than the median 4.48, so where I positioned it probably isn't exactly to scale. Okay, but that's just the information up here, the mean Q1, Q2, Q3. Okay, and we could do that for all of these, locate the mean with respect to the median 4.49, just above the 4.44 median. Over here, the mean is 4.13 versus the median is 4.08. So these plus signs then refer to the placement of the y-bars. So if I have these 3 different groups and I'm looking at their box plots, I get some information for how the y-bars compare to each other from one group to the next, as well as how dispersed the data are. Okay, in this middle case, the maximum score is given by this bar up. The whisker is extended to the maximum score, and down here to the minimum score. Okay, depends on the software, and you can choose some different options. The length of the whiskers sometimes are functions of the interquartile range, and it just depends on the again the software used to create that, and so I didn't fully investigate that here. Okay, when you have some extreme scores relative to the amount of variability here, so the extreme scores are sometimes marked then by other symbols, in this case a square, sometimes asterisks or other points. All right, so here's the maximum value here, and here's the minimum value here. Okay, and so the length of the whisker is sometimes referred to the whisker is drawn out to the last observation within 1.5 times the interquartile range. So, so here the interquartile range is quite large, and then, and I'm not sure this to the last score within that range. So this would be the second highest score here in this case. So you can change those. The whiskers can be drawn to the maximum, and to the minimum is the default, but I say oftentimes it's some sort of function of the interquartile range. Okay, but again, the idea is at a glance we can see how the y-bars compare. We can see that this group tends to have a much lower variability, say, than group 2. Okay, so that if we have, once we get into some other procedures where we come to some conclusions about comparisons among these groups, the box plot may help us illustrate those differences. Stem and leaf plots are a stem and leaf display, and so we define a digit to be a stem digit, and then we have a leaf digit, or a finer digit is the leaf. All data values are displayed. Therefore, it's kind of limited to keep it to smaller data tables with a stem and leaf display. We can observe location location is another way of saying measure of central tendency. Where's the data at? How dispersed the data are, and also the shape of a data distribution. And we'll talk. So with graphics, we get into the shape of distributions a bit. Suppose we have our sample data set given here. Everything is 2 digits, so there's no commas in here. And we count things off here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 data points. It says our sample data set, so therefore I know I'm lowercase n equals 15. And the idea here is most of our data, we start in the teens, we go up to 59, looking at this, and so that we want to sort our data, we form a stems digit, and so that was, for this one, looks like it would be the tens digit, and you could either start it at the top or the bottom, so I'd have 10, 20, 30, 40, 50, okay, and then start working your way through the data. So we have, then if I put a 7 here, this is the stem digit, and this is the leaf digit. Okay, our stem digit we specify as 10. Okay, so that means this is multiplied by 10. Our leaf digit is 1. Okay, so it's going to be 10 times 1 plus this, 10 times 1 plus 7. All right, so that's our 17. Then we have 39, 34, 21, 29, 47, 54, 22, 28, 39, 46, 22, 31, 43, and 59. Count here: 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I got them all. Okay. Now they're not in order, so the next step, then we want to sort or order the leaf digits within each stem. So I still keep the 10, 20, 30, 40, 50. Well, there's only one teen, so the 17 stays the same. Now put these in order. So I'd have 1, 2, 2, 8, 9, 1, 4, 9, 9. In the 40s, 3, 6, 7. In the 50s, they're 4 and 9. All right, so now then within each row, the leaf digits are in order, hopefully. We can repeat our legend over here. Our stem digit equals 10. Leaf digit equals 1. Okay, and then you can look at this, and so if we have 15, the 8th ordered score is the median, right? Okay, so from either end you could count 1, 2, 3, 4, 5, 6, 7, 8. The median is 34. Okay, you also get the idea of the shape of the distribution if we were just to say to draw a curve over how the data are distributed. And so descriptions here, most of our data tend to be in the 20 or 30s. We're seeing that's kind of where the peak. If you were to identify a mode, could we do that easily? Sure, because we haven't lost the data by a symbol. The data are still here. We have 2 22s and 2 39s. So we have a bimodal distribution, right? Okay, so it lets us see how spread out the data are, where the peaks or most frequently occurring observations are, which most frequently occurring stem, if that's important. If our stem digit were 100 and our leaf digit were 10, then this would be regarded as 170, right? Okay, so you can represent different scales. If our stem digit was 0.1 and our leaf digit was 0.01, then this observation would be 0.17. Right? Okay, so that's why you need to have a legend here for these. If you have a very large data set, and suppose then we end up with these very long rows then for each of these tens, then you may end up maybe having, say, a 1 and a 1 a 1 star. So the ones may be 10 to 14, and then 15 to 19 are in the second half. And so you can break things down like that too. Okay. If all of your data tended to be in the teens, all right, then you look at a finer definition perhaps of the stem digits. So there's lots of different ways you can do that. But the idea here is that I still have all of the data. Typically when I draw a graph, I don't have data anymore, right? I've got this image, and so I have these summaries up here, but I don't have the data anymore. So stem and leaf display is a way you can still get things visually, but you still have the data. Probably you're not going to show this in a presentation, but as you're working with things, trying to develop some diagnostic tools to help you make some decisions and so that you can write a more informed statement about your data set, a stem and leaf display is helpful to you. Probably not so much your reading audience. Okay? Box plots and other kinds of graphics you'd want for your reading audience, right? Scatter plots. If you collect 2 or more numeric variables in each record and you're interested in how these things occur together as a pair, then you can use a scatter plot. So we can allows us to check for a relationship between pairs of variables. So if we plot our ordered pairs of data on an XY coordinate plane, okay, so since it's both X and Y here, we have X, Y here, X ranges from 2 up into the teens, Y ranges, we got what, 1 up also to teens, so it could go 0, and I scaled mine by 2s. I think on both axes I did. All right, and if we're going to do Y versus X here, okay, so X goes over 7, up 18. You guys have likely done this before. X equals 8, Y equals 19. X is 12, Y is 14. So X direction. X is 2, Y is 18. X is 13, Y is 10. X is 17, Y is 4. X is 11, Y is 11. X is 18, Y is 2. X is 17, Y is 1. Whoops. Gotta unclog my pen. All right, so the idea here is that we see an association between X and Y. How would you describe it? As X increases, Y decreases, or a negative association between them, right? Put another one here, X versus X on the horizontal, Z here. Keep the same scale for X. Z ranges from what? 0 to 2? To about 0.2? All right, so we probably did all this kind of stuff in college algebra. Just make sure as you move across here, we've got X and Z, so we're staying in the first and third columns. So we have 7 and 0.5, 8 and 0.6, 12 and 0.8, 2 and 0.3, X is 13, Z is 1.1, X is 17, Y is 1.8, X is 11, Y is 0.9, X is 18, Y is, Z is 2. I said Y on the previous one, but I plotted Z. 18 and 2. X is 17, Z is 1.9. All right, so here we have a different type of an association that as X increases, Z increases. And so what we'll get into later perhaps with these is discuss how do we measure the strength of that association. Okay, if we want to use a predictive equation, if we know X, can we predict Z or can we predict Y? And we'll get into that towards the end of the course. Bar charts. Pretty sure everybody's comfortable with this because I know my daughter's done this in 3rd grade. So, all right. In the bar chart, we illustrate the frequency of the values of a qualitative or discrete numeric variables, and so frequency is just simply the number of times the value is observed. All right. The length of the bar indicates the frequency or relative frequency. We'll talk about both of those. And so the idea here is if, say, we're measuring something such as eye color. And we have our, say, brown-eyed individuals, blue, green eyes, and other, the hazels, the violet, and all the Liz Taylor and her friends, right? Frequency. So we measure this, say, for a sample. Whoops, how about 3, 4? I haven't given you any data, so clearly I'm just making something up. So here, so the bar height, suppose in our sample we have 6 brown-eyed individuals. Our blue-eyed individuals, we have, say, 3. The idea behind a bar chart, though, is you have these discrete values down here. There's nothing connecting the bars. You can put the bars in any order. Typically, if you have an other category, it's always the last thing that occurs. But our bars are generally the same width. There's not an idea of a continuity across this x-axis. The frequencies here can be the actual counts or the relative frequency. Relative frequency means out of how many. So that if we had 6 out of, how many do we have here? 6 plus 3 plus 1 is 10 plus 3 is 13. So this height would be 6/13, whatever that decimal equivalent would be, etc. Okay, so we all know what bar charts are. Histogram is used whenever the value on the x-axis is a continuous variable. And so the height can still be frequency or relative frequency. And so the histograms then usually we don't see the spaces in between bars, and it makes sense the order the bars occur in have to be specific to the order of the variable on that x-axis. Okay. Whenever we create a bar chart or a histogram, unless something occurs with frequency 1, we are sacrificing the data, right? If that's all we see, okay, if that's all we show to someone, or if that's all we receive, we don't have the data. We just have a summary of it, okay? And so what's important here with the histograms is that we're looking at continuous variables, okay? We want to break up our continuous variable, the range of those values, into different class intervals where these class intervals are the same length. We identify a midpoint for each of those class intervals, and then the f sub I is the frequency, the relative frequency is the frequency divided by the sample size. and we have that the relative frequencies, the sum of the frequencies over the sample size, that's got to be equal to 1, but across all the different values of I. Okay, and so we again construct bars of an appropriate height. So suppose you have some data then that look like this: salary of 79 teachers. Okay, so at the midpoint here, we construct these classes, so the 25,000 up to, but not including 30,000, and 30,000 up to, but not including 35,000. So the left-hand endpoint here, each of these are 5,000 apart. That's what we mean by intervals of the same length. Okay, and so that the midpoint for each interval, when I move from this to this, the midpoint in between this, the halfway point, is that 27,500, right? Okay, that's the interval midpoint here. So all 5 of our scores that we measure in this interval are all going to be regarded as 27,500. Numerically, that's all what we're going to do. Okay, so what would be our next midpoint for this interval? What's the midway between here and here? 32.5. Heard someone say. Everyone agree? Loudest vote wins. All right. And for the 35,000 to up to 40,000, this one's going to be 37,500. And next, 42,500. 47,500. And this last one, it says everything over 50,000, but we keep, notice our midpoints are 5,000 apart, just as our left-hand endpoints are here. All right, so keeping that interval of 5,000 then in there, then there's the 52,500. Okay, these are the frequencies or the observed values. So it says of 79 teachers. So if you go through your sample and you classify, you have each of their individual salary information, but you put them into these different classes. Or more likely is the case, if you survey someone, they're not going to tell you specifically, but they may likely check a box for their range, or they may not answer you at all. Okay, but the sum of your frequencies here should be equal to n always. Okay, and for us that value of n is 79. If you compute a relative frequency, again that's frequency divided by the sample size here. So if just writing it as fractions doesn't seem, so the 5 over the 79, if you write the decimal equivalent of that, that can help you establish a vertical axis on your relative frequency histogram. Okay, 17 over 79, 24 over 79, 18 over 79. We'll come back in and we can compute those maybe to 4 decimal places. 12 over 79 and 3 over 79. If you add up the total of these, that should add up to 1. Okay. Zero 633. 0.2152. 24 divided by 79. 0.3038. 0.2278. 0.1519. 0.0380. Okay. Now, if we look at these can we talk about a median class? Can we talk about a modal class? Can I find a median score? No. Because median score implies I have all the data. I just have a summary of the data. So can I find a median class? Yes. So the median class then is in which interval does the what score? So we have 79, and so the median is going to be in position what? Sample size is odd, n plus 1 over 2, right? The position of the median is equal to the 40th score. Are the data in order? Sure. Yeah, we've got the bars in order, okay? So it doesn't matter if I start from the low end or the high end. Where's the 40th score? I've got 5 here, plus another 17. I'm up to 22. Okay, 22 plus this 24. Okay, the 40th score is in this class, right? So all I can really say here is that this is the median class. Could I talk about a modal class? Which class is the mode? Same one, because that's where the highest frequency is, right? Now that doesn't always happen. Okay, it does in this illustration, all right, but that doesn't always happen. Okay, form a relative frequency histogram. Okay, so the idea behind a histogram versus a bar chart, boy, already. So in a histogram, we want to look at things. Here we have, I'm off screen reading my relative frequencies. 0.06, 0.03 is our lowest. So so we could put things, say, in a 0.05 intervals, 0.10, 0.15, 0.2, 0.25, and 0.3. So this is our relative frequency. And then you can draw bar heights above things here. So we have some beginning at 25,000. The bars are centered at those midpoints. All right, so this 27,000 has a height of 0.06. 30,000 to 35,000. Again, I'm reading a value that's off screen here, but that's 0.2152. Now you're going to get something prettier off of a computer output, surely. Okay. 35,000 to 40,000 is 0.3, just over. But the idea is that, is that the width of the bars are the same, 40,000 to 45,000, 0.22. 45 to 49, 0.1519. And then 0.03. All right. Hurried through that a bit, but we end up with these values here. And so I'm interested in this silhouette or shape. Okay, kind of the shape of the bars indicate the distribution of the data. All right. We can also see at a glance here which the modal class is, because that's where the thing peaks. All right, so we want to do some more things with the distribution of the data. All right, but so we're interested oftentimes in whether this has a symmetric look to it, how sharp the peak is, how broad the peak is, where is the peak. And so we are very concerned with the distribution of data sets whenever we measure data and collect that in our experiments. And so there are some terminology then associated with shapes of distributions. When we talk about kurtosis, kurtosis then refers to kind of the peaked nature of the distribution. And so if the general silhouette then kind of, if it flattens out at the top and comes back, that's referred to as platykurtic, the idea that you see somewhat of a plateau in your data. If you have a distribution, all I mean by this is we have an x-axis and it's very peaked in nature, not quite as, then that's referred to as leptokurtic. And some of the social sciences is where I tend to see that there are some computations that are measures of kurtosis that assess these two quantities numerically, but so we don't go into those here, but there are some measures of kurtosis that one can compute. Skewness, when we talk about data being right skewed, what that means is that we see the peak of the distribution and it tails off to the right. There's those few extremes. So right skewed would be the example of those salaries that we talked about. You know, most of us are over here and there's one or two that got the really good high-paying job. Left skewed would tend to be then the mirror image of that. You have low, very few observations in the left-hand side, and then the bulk of the distribution is off to the right. Okay, so the direction right and left in the skewness determinations, that right and left refer to where do the extremes lie, to the right or to the left. We can talk about symmetric or mound-shaped distributions. That's the one I tend to draw most in this course. Oops, not quite so flat at the top, but this also referred to, perhaps you've seen people talk about bell curve or the normal curve. And so when we look at a symmetric distribution, so we see a mode and then kind of on either side of that, then it's one side's the mirror image of the other. And so that would also tend to coincide with a median if it's is indeed symmetric. Now, whenever we look back at this display here, all these bar heights for a relative frequency histogram add to 1. Okay, so it is the case when we talk about distributions that kind of the areas under here add to 1. All right, and we'll see more of that coming up. Okay. We want to talk briefly about the empirical rule. Again, we don't do a lot with it here in this course, but if we have a mound shape or symmetric distribution, such as the last one that I illustrated, we can talk about what fraction of the data lies within specific intervals around the mean. So remember here our mean is given for the population is given by Greek letter mu. Our standard deviation for the population is given by Greek letter sigma. So the idea here is that if you have a symmetric distribution, the mean is also going to be in the middle. So mean, median, and mode are all right there in the middle. All right, if you go forward one standard deviation to a point mu plus sigma and back the same distance, okay, and if I'm a really good artist, this looks like the mirror image of this. Okay, this area here is the mirror image of this, and I'm not so good today, but all right. But what we're saying then is, if we have these symmetric distributions, it is the case that within one standard deviation of the population mean, that if we were the idea that if we had all those bars indicating relative frequency, 68%, or this area in between here, would be equal to 0.68, or you can write that 68% of the data is from here to here. And so that means then that 32% would be out in the tail regions of that distribution. Okay, whenever we look at the distribution, see if I draw it a little better this time. I don't know, bigger, but not necessarily better, I suppose. All right, so we have our population mean. We move forward 1 standard deviation, then plus 2 standard deviations, likewise. Back 1 standard deviation, backwards 2 standard deviations. Okay, then the area from here all the way over to here, we're taking in approximately 95%. Without drawing it, if we take this out in 1 more standard deviation, we capture all or almost all of the data. So different references will say that. We'll say at least 99% or something, but the idea that you'll get all or almost all of the data. Okay? So the empirical rule applies to just these symmetric distributions and not to anything that's skewed.